Now we'll see the stereochemistry of penicillin. We have known the structure of penicillin, okay. So what is that? It is having a beta-lactam ring that is fused with the thiazolidin ring, okay. Before going to see the stereochemistry, first we have to find how many chiral carbons are present in penicillin. What is meant by chiral carbon? That is otherwise called as asymmetric carbon, and that should have 4 different groups. First look at this, this is sulfur not having carbon, okay. Then this one, second position we have carbon and that is connected with 2 methyl. So these are similar, that's why it is not a chiral carbon. And look at the third one, here it is connected to one H, COOH, and here the left group and here left group. So different groups, 4 different groups are attached with this carbon, that's why this is a chiral carbon. And here carbon is not present here, and in this position here one NH, another end this end, this end, this end. So 4 different groups, that's why this is also a chiral carbon. And look at this one, so here H, R, CONH, this part and this part, so this is also a chiral carbon. And look at this, here 2 bonds are connected with oxygen, here one, so it is not a chiral carbon. So totally the penicillin, no, that is having 3 chiral carbons, 3, 5, 6. So these 3 carbons, no, these are considered as chiral carbons. These are considered as chiral carbons or asymmetric carbons, okay. So the stereochemistry, this would be the stereochemistry of penicillin. So what is that here? What is the meaning of R and S? Already we have known about configuration. What is meant by configuration? Spatial arrangement of atoms or groups in a molecule can be called as configuration, and this can be broadly classified into 2 types, that is absolute configuration and relative configuration. Okay, here this is relative to D-glyceraldehyde. So there may be 2 types, D and L. Here absolute means R and S. So the absolute stereochemistry of penicillin is 3S, 5R and 6R. All the naturally occurring and microbiologically active synthetic or semi-synthetic penicillins, no, they have the same absolute configuration about the 3 centers. Here the carbon, this carbon, no, carbon having the acyl amino group, that is having L configuration. Here the carbon having, that is carboxylic group, no, that is having D configuration. And this is having alpha orientation relative to Pnum ring. This one, no, this is having alpha orientation. What is meant by alpha? That is indicated as a dotted line, here the group attached below the nucleus. So this would be having alpha orientation relative to Pnum ring, and this is having beta orientation. Beta means that is indicated as a thick line, here the group attached above the nucleus, okay. So this is beta, this one is alpha and this one is beta, so that's why both are trans to each other. So this is the stereochemistry of penicillin, okay. Now we'll see the mechanism of action of beta-lactam antibiotics. Before going to see the mechanism of action, first we have to know what is meant by peptidoglycan, okay. So what is peptidoglycan? It is otherwise called as murin. It is a structural component of bacterial cell wall. Actually it is a polymer, and that is having sugars and amino acids. What are the sugars present here? This is having alternate residues of beta 1,4 linked NAG and NAM. What is meant by NAG? N-acetyl glucosamine and N-acetyl muramic acid. So it is a polymer that is having sugars and amino acids, and they form a net-like structure, that is a mesh-like structure that surrounds bacterial cell wall. What is the use of peptidoglycan? That one is giving strength and rigidity and counteracting the osmotic pressure of cytoplasm, and important for binary fusion during bacterial cell reproduction. So what is meant by peptidoglycan? It is a structural component of bacterial cell wall, and it is made up of sugars and amino acids forming a mesh-like structure that surrounds the bacterial cell and is important for strength and rigidity. That is about peptidoglycan. Now we will see about penicillin binding protein. They are otherwise called as DD peptidase or DD transpeptidase or D-alanine, D-alanine peptidase or penicillin binding protein. So totally 4 names it is having. What are they? DD peptidase, DD transpeptidase, D-alanine, D-alanine peptidase, and penicillin binding proteins or PBP. What is the action of penicillin binding proteins? Actually they are bacterial enzymes present on cell membrane. What is the use of this one? That is responsible for cross linkage of peptidoglycan, okay. It forms cross links with the peptide bond of peptidoglycan strands and responsible for biosynthesis and cross linkage of peptidoglycan. In that procedure, here one procedure is used, that is called as transpeptidation. That's why they are called DD transpeptidase. By that procedure what happens? There may be removal of one molecule of D-alanine. Okay, so this is the use of penicillin binding proteins. What is the use of penicillin binding proteins? They are responsible for biosynthesis and cross linkage of peptidoglycan by means of a procedure called transpeptidation. What is meant by peptidoglycan? They are a structural component of bacterial cell wall, and that forms a net-like structure that surrounds the bacterial cell wall, and that is responsible for strength and rigidity. Okay, now we'll see the action of beta-lactam antibiotics. Okay, now they are binding with the proteins. What are the proteins? That is DD peptidase or penicillin binding protein. So it is binding with the proteins. How it is binding with the proteins? It will acylate that proteins and inactivate them from forming peptidoglycan. That's all. So what is the action of beta-lactam antibiotics? They are binding with the proteins. How it is binding? That is, it is acylating the bacterial deep transpeptidase. By means of that acylation, it inactivates them from forming peptidoglycan. This weakens the bacterial cell wall. That's all about the mechanism of action. Now we'll see the advantages of semi-synthetic penicillins. Already we have seen the examples of semi-synthetic penicillins. So these are the advantages. The acid stability would be increased. They can be taken orally because of the resistance to stomach acids, and now because of that they have better oral absorption, and they are having broad antimicrobial spectrum, and they are having increased activity against resistant microorganism, and they are having decreased allergenicity and increased tolerance. Now we'll see the SAR of penicillin. So we'll see the SAR of penicillin. We have known the structure of penicillin. So what is the first point? So we have to tell this one. So here we have known this is a beta-lactam ring, and this one is fused with a thiazolidin ring. So that would be the first point. We have to tell about the structure. So it is having a beta-lactam nucleus. That one is fused with the thiazolidin ring. So that is the first point. Okay. Now here what is attached in first portion? First portion we have sulfur. If the sulfur is oxidized to SO2 or SO, SO2 is called sulfone. Already we have seen sulfone in dapsone. What is meant by sulfone? That should have S, that is connected with two oxygens by means of double bond. Okay, S double bond O, S double bond O. That is called sulfone. Sulfone or sulfoxide. If the sulfur is oxidized to sulfone or sulfoxide, what happens? The acid stability, that is increased, but the antibacterial activity, that is decreased. So what is the action of oxidation of sulfur? If it is oxidized to sulfone or sulfoxide, what happens? The acid stability would be increased, but the antibacterial activity would be decreased. Okay. Now we'll see the second portion. Second portion we have two ethyl groups. They are essential for activity. There should not be any substitution in the methyl group. So this is important for activity. Now in third portion we have carboxylic acid group. So this is important for activity, and this carboxylic acid, that should be free. It should not be converted to alcohol or ester. If it would be converted to alcohol or ester, what happens? The activity would be reduced. Why it should be free? Because the binding site is having lysine residue. That one is having positively charged ammonium ion. So that is having plus charge. Okay, if it is free, then only it will be converted into carboxylate ion, that is having negative charge. So this negative charge can easily bind with the positive charge of lysine residue. That's why it should be free. Okay. Now in the fourth portion we have nitrogen, that is important for antibacterial activity. And come to fifth portion. Fifth portion, there should not be any substitution in fifth portion, because already we have seen three chiral carbons. Where are they? One at 3, 5 or 6. Okay, so here if it is this is also a chiral carbon, so here it is connected with one hydrogen, so it should not be substituted with any other groups. Okay, because of the chirality. Okay, if we need chirality, there should not be any substitution. If there is any substitution, the activity would be reduced. Now come to the sixth one. So before that we'll see the seventh one. So what is that? We have a ketone at seventh portion, and that is important for activity. And we have acyl amino group in sixth portion. That is very, very important. So this part now, acyl amino group is responsible for solubility and physicochemical properties. And in that we have R. This R depends on acid stability, and by means of R only we can tell whether it is susceptible or resistant to beta-lactamase, that is penicillinase enzyme. If we have electron withdrawing group in R, means what happens? The chance of acid hydrolysis, the chance of acid degradation, that would be reduced. For example, and increases the stability and oral bioavailability. The example would be ampicillin, that is having electron withdrawing group, that is NH2 in R. Okay, and if we are increasing the steric hindrance at R, what happens? What is meant by steric hindrance? Introduction of bulky group that can be called as steric hindrance. Okay, if we increasing the steric hindrance at R, what happens? the resistance to beta lactamase would be increased. Example would be methicillin and nafcillin. Okay. And next one, if we introduce a hydrophilic group in R, what happens? The gram positive activity would be increased. The examples for hydrophilic groups would be NH2OH, COOH. The example would be ampicillin. Then if we introduce the strong acidic group in R, what happens? The broad spectrum activity would be increased. Example, ampicillin and ticarcillin. If we introduce urea group in R, what happens? That results in broad spectrum antibiotic activity, okay, and that is active against Pseudomonas aeruginosa. Example would be uridopenicillin, in that mainly acetylcysteine and piperazillin. And the last one, we have to keep the pH of the penicillin between 6 to 6.8 by means of refrigerating them. Okay, if we are keeping them, means the degradation of penicillin can be retarded. Already we said it is having 3 chiral carbons. Where are they? 3, 5 and 6. So that the 3 chiral carbons, no, they are very, very important. So where are they? 3, 5 and 6. If there is any change in spatial arrangement of that, what happens? Activity would be reduced. That's all about the SAR of penicillin.